Hi, Shane.
Hey, how are
How
you?
are you?
I'm good.
Good. All right, let me share my screen.
Mhm. All right.
Yeah.
So when
I
you
mean,
test, you like took like the CP section and then the break, and then
Shane, I took all of them in the correct order.
yep.
I sat down and I took it. I started a little bit after 3. That's why I wasn't answering your text right away. I wasn't done when you were texting.
So yeah, that's pretty amazing. You completely rocked it. Congratulations.
Went down like a Reddit hole after I finished yesterday, and it was saying that the like cars section is super inflated and that it's not like a realistic estimate, but it did say that the CP was harder than normal, so me getting
Mhm.
I don't know. And then I've never left questions blank, but I figured because we'd go over it and I like literally had no idea. I don't know, it was just better not to guess because sometimes when I guess I get them correct and that's not
I see, I see. Yeah.
what
On
I
the
right
actual
now.
test though, you want to
Yeah,
make
obviously. I never leave anything blank ever. So, all right. I mean, this one I understood because
Mhm.
I can't remember where it was. There was a part of the passage
Mhm.
that was answering this.
Yep.
Okay, well, basically, like if it's used to treat an HIV infection, it's like an antagonist of the HIV virus.
Mhm.
So, yeah, that's fine.
Yeah, they say down here that it's a protease inhibitor. So it,
Yeah. So I was confused with this one because I literally started counting out like every single
all right, so
figure out where the stereoisomers were, and I got this one, like that 1, 2,
So
3.
the st so to answer questions like this, um, we just count the number of chiral centers, and a trick for that is if you see like a carbon attached to like a wedge of some sort, that must mean that
That
that's
it's
a chiral center.
so
Um,
that we have 1, 2, 3, 4, 5.
um, yeah, and uh so now in at each chiral center, right, you could have the wedge, a dashed wedge, or you could have a black wedge. So that means that, so like you said, 5, 1, 2, 3, 4, 5. So like
Mhm.
how many options are there for the first one? It could either be black wedge or the dashed wedge. So two options. The next one, same thing, two options, two options, two options, two options, right? So it's really going to be 2 to the n power, where n is the number of
5.
chirometers. Yeah, so this will be 2 to the 5th
Hmm.
power. So that'll be 2 times 2, which is 4, times 2,
That's
which is 8, times 2,
16,
which is 16, times 2,
32.
32, times 2, which is 64. I think it'll be 64.
Yeah.
Oh no, 32. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So
Right.
1, 2, wait, 1, 2, 3. Am I seeing something here? 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2. What am I doing here?
Because both of these twos go into the 4, right? So there's only 3 other ones.
Okay. Yeah, yeah. Oh, that is 32.
Yeah.
Oh, okay. I don't know why I thought it was supposed to be 64 or something, but okay, yep. That's how you do that. Okay, so remember when we did all of the K stuff? All of the K stuff is derived from, the law of mass action that states that it's like the product concentration over the reactant concentration. But what you do with the product concentrations is that you multiply them, you don't add them.
So it's B.
So yeah, it'll be B. So first we could eliminate A and C because we don't ever add them like that.
Okay. And then
Yep.
how do I know which one? Oh, so in Q is thermal like potential energy or something.
In this context, it's going to be something called the reaction like quotient.
Okay.
Basically just like K, except, not at equilibrium. But so yeah, so we can eliminate the ones with the plus signs in them, and then we have the choices where they multiply them correctly, but would it be below KSP or greater than KSP? So the KSP value, right, is the largest concentration that can be soluble. Um, so if your Q, your reaction quotient, if that's larger than your KSP, it's going to uh be like less soluble and therefore produce a precipitate. So KSP is really just a value that means it's the maximum, you know, concentration at which uh something can be soluble.
Okay, here's my question. Is if it didn't say these answers, like if I was just looking, I would never have come to the conclusion to write out this and use the like whatever, the law of mass action.
Mm-hmm.
Like how do you look at compound one and derive these? Like I don't even see calcium in it.
All the way on the bottom, it seems like first sentence on the bottom. Right.
Oh, okay. Calcium oxalate. Okay.
Yeah, so remember how we talked about like how like certain things are salts and if you put it in water it dissociates
Hmm.
and to be able to see what it can dissociate into. So this is so we should know that calcium would dissociate into calcium 2 plus. And then the C2O4 would have to be a 2 minus charge, right?
Hmm.
So yeah, so that's so like in K expressions, like you're always going to be doing like the product over reactant, but for KSP in particular, which is solubility, uh since your reactant is going to be a solid, that means that we don't include the reactant in that expression for KSP, but
Okay.
yeah, you'll be uh multiplying them to get your
Okay, so
uh-huh.
if I see KSB, then I know I need to be multiplying the product in the solution.
If you see K anything,
K anything, it's always a multiplication. It'll never be addition.
correct.
Okay. Then between D and B, I know that it has to be greater because no precipitation would occur if it was less than KSB.
Uh-huh.
Okay, let me
Yeah.
write that down.
Yeah. Think of KSP as the maximum concentration at which it remains soluble. Therefore, if Q is greater than KSP, it will stop being soluble and start precipitating.
Wait, Q is greater than KSB.
Yeah. So
It was always greater than KSB.
no. So Q could be less than KSP, it could be equal to KSP, it could be greater than KSP, right? But If
But for it to be soluble, Q has to be greater.
So KSP is the max amount for it to be soluble. Therefore, if Q is larger than KSP, it will cease to be soluble. So you could say, so you could write this like Q less than or equal to KSP will be
Soluble.
and if Q is greater than KSP, insoluble. So
Okay.
yeah, Q is just a way of us describing a reaction when it's not at like equilibrium or not at a K value. And so it can shift in whichever direction that it'll go to like remake the equilibrium. So, but I know it could be, kind of confusing because we talk about Q in physics and Q here and stuff. So
So many different Q formulas in this exam. There was like a Q equals MCAT formula, and then there
yep,
was the thermal one.
yep. Yeah, I'm surprised they don't use more like different letters, like Z or something. But okay. Let's see.
I
Nine.
got, I think, all of the amino acid ones wrong.
Um, well, so let's see, right? So let's take a look at the compound or whatever. Where is it? Oh, is it above this over here on the left? Yeah. So check this out, right? So yeah, so okay, I'll write this down to something to like.
Like, I recognized that this was phenylalanine.
Yeah. So now, um, so now peptide bonds, like when amino like when two like amino acids form a peptide bond, that bond is gonna have what's up?
Is this supposed to be proline?
Mm-hmm.
Hmm.
Yeah. So yeah, see what I mean in terms of like when you're showing me like your notes on this and like how so like and how it appears here is different, right? It doesn't say like CH2, right? So
Yeah.
but yeah, so
Proline, I always draw like a house. I just ready to start drawing them out and practicing more.
uh-huh. Yeah. Because yeah, the drawing it like this like saves you a lot of time as well because you don't have to draw each of the CHs and stuff. Um, but But so proline, more than one amino acid has a ring, right? But
Right.
proline is unique in that its ring incorporates the backbone, meaning so like uh
It's a
so
phenylalanine too.
well so okay so let's
Sorry.
so for the so okay like be able to draw an amino acid like let's say with this R group here and then the
NA.
carboxylic acid group there. So this is just a regular generic amino acid backbone, right?
Yeah.
Okay. Now, um, okay. Now, if the R group here is, a benzene, right? That'll be
Or like tryptophan or
phenyl alanine here.
that's
So yeah, I'm missing a carbon here, but it would be like this. Okay. So that's phenylalanine. So you see that there's a ring, and the ring is
it's a circle.
attached to that R group. Now, there's also, as you said, tryptophan, but that will just be similar to the phenylalanine in that it's in the R group specifically. Now, the thing about proline is it's a ring that it forms between this, the R group and the amine.
Mhm.
Okay. So like, something like that. So that's why here we see that the ring is attached to its own amine. You could also see that as it's the only amino acid that has a secondary amine, because every other amino acid just has a primary amine, which means it's a amine group that's attached to carbon, but this time it's attached, like it has two bonds to carbons. So proline creates like kink or creates like
Yeah, it like can't fold correctly because of it, right?
yeah. So okay. Now yes, okay. Alanine we have our peptide bond, aka an amide bond, right?
Mhm.
We have this, which is CONH3. So what do you think that could look like? That could also be good practice to be able to see like what a CONH2 thing could look like. So how to do this? We want to first think about how many um how many um
And then the H's are bonded, so then
how many bonds can carbon make?
4.
Yep. So this, so carbon here already has a bond here, you know, and we want 3 more bonds, right?
Like that, no?
Like what you drew? Is that's an O and then this is an N here?
Mhm.
And so
Then
we're
it wants to have 2 of each. Or no, it wants 3.
where's the carbon here? So this looks like an oxygen and then nitrogen here.
But isn't the carbon linked them?
Uh it seems like what you drew is a bond between oxygen and nitrogen. Um but what this could look like would be the carbon double bonded to the oxygen, because we know that it likes to do that, and also bound to this NH2 part,
Mm-hmm.
right?
All right.
So um so yeah, so this would just be that, right? Are you there? What are you thinking?
Are there extra like carbon bonds not like is that fine to have?
Uh
I thought like I don't know. I guess I thought when you're reading it that like if there's only one carbon like written that you can only have one carbon.
mhm.
You have 4 extra ones now.
Wait, 4 extra carbons where?
Okay. 1, 2,
So,
3,
oh,
4.
there's just one here. These lines are bonds.
Okay. All right.
Sorry. So like I this is so here, so this squiggly line here just means that it's the one that's attached. I'm only considering like this over here.
Mhm.
Like this squiggly line is this squiggly line. Like I
Okay.
am just
All
making
right. Sounds good.
that. But
I
but
get
I think what you're kind of asking is like, so like for instance, if I drew ethane, like CH3 bound to CH3, that would just look like a line like this, right? So, but if we have like, actual like atoms between these, like if we had like you know, a C and I don't know, like a Cl or something, then this line is really now just the bond between the C and the Cl, right? But if I do like another line like this without writing an atom at the end of that line, then it's implied that this is the CH3. Yeah. So I think it's just this type of notation that you can practice. I'm going to write it down too. But that's an easy fix. That's an easy fix. So
All right.
so we have,
So
yep.
looking at this problem, well, whatever they give, but it's phenylalanine and proline, but
Mm-hmm.
do you see how it gave the pH? Would it do that for the other ones for like valine and alanine if it was there?
No,
No.
fortunately. They do the pH just because it saves time in drawing the entire benzene group.
Okay.
So, but yeah, so we have our, phenylalanine. We have some, this is another amide here. So this is going to be something like glutamine or asparagine. And then we have another phenyl here, phenylalanine here. And we have our proline here. And then here we have another amide type of functional group. So that could also be like, asparagine or glutamine. And then here we have something that could be more like one of like the non-polar ones. But yeah, they're asking us, so if they're cleaving it here, what are we, separating? And we're separating the phenyl part from this proline part. That's the peptide bond that we're cleaving.
Okay.
So
Wait, yeah, this is what I wrote, but I wasn't like,
yeah.
I feel like this is just a way that like crossing the membrane usually goes where there's like a certain concentration, like this is the gradient and it's harder for it to pass from extracellular into it. So
So
it'd
these
be going,
are electric field lines, right?
yeah.
So they're not really like
So
depicting.
like a bio question, but
Wait, what?
I don't know. I didn't know like what the rules were for like electron gradients, so I just used it from the context of like biology, like cell membrane.
So the thing is that things aren't really moving here.
Hmm.
So but they're asking for the electric field lines, right? So like so what can you tell me about like, a neuron like depolarization, blah blah blah?
A neuron depolarization.
Yeah, you know what I'm talking about? Like action potential, depolarize.
Like I think so, but I don't know how to answer your question.
Oh, so I'm just asking, like, what can you tell me about, um,
About action potential.
yeah, that topic? Like,
Isn't it the potential to do work? Like it like
like this thing?
kinetic energy. Yeah, and it's like it's something needed to cross over this part, right? It's for it to go.
So what I'm
Is
talking about,
there like a point? This is like, oh no, I'm thinking of Cam.
hey, sorry, what's up?
I'm not sure.
Oh, so yeah, no, so neuron, so
Action potential, it's not like the Vmax, any of that stuff. That's what I started to talk about just now.
oh, that's like enzyme kinetics,
Yeah.
but so this is basically like how how our like neurons work. How do we like you know pass things along through neurons?
Right.
So basically, you're inside. Let's say this is the inside of a neuron, right? You're going to have a high potassium concentration relative to the outside, low sodium ion concentration compared to the outside, where outside it's low potassium, high sodium, right? Now, this shouldn't be the case because this should achieve equilibrium, meaning the potassium should be leaving the cell and the sodium should be entering the cell, right? Are you there? Are you like,
Yeah,
okay?
I'm just,
So so that's what should happen to achieve equilibrium. However, it does not happen like that because of a sodium potassium pump. And what that does is it takes in two potassium ions and it spits out three sodium ions. Okay.
mhm.
So that means that it's overall losing a positive charge, which means that this a neuron's like resting membrane potential is around negative 70 millivolts down here. Now, if an action potential, reaches the threshold, it'll open up sodium channels. And so I'll use green. So if you opened up a sodium channel here, which direction will sodium go? Will it come from the outside into the cell, into the neuron, or
Wouldn't it want to go into the opposite direction that the pump was pushing it through?
uh-huh.
If the channel opened up, it would want to go to like wherever there's less like of a concentration of them.
Yep. So for sodium, would that go inside, outside?
Um, Outside.
So
Because if there's low K here.
sodium though.
Oh, sodium would want to go inside.
Exactly. Sodium goes inside, and that's we call that sodium influx. And that's what happens during this depolarization phase. Because if you're having an influx of positive sodium ion, the resting membrane potential goes from negative 70 all the way up to like positive 40,
Okay.
right? Okay.
Should I know these values?
Yeah. You should know
Okay.
like every kind of step of the depolarization repolarization thing. So this is when the sodium channel opens up, right? Now at the top here, the sodium channel closes,
Mhm.
but now the potassium channel opens up.
And it's the opposite.
Yeah. So which direction would potassium be moving?
Potassium would be moving out of.
Exactly. So if it's moving out, and that means we're losing that positive charge, we're starting to get less positive, right? And more negative. So we're going back down here, which is called repolarization. And the potassium channel is slow, so you're gonna get a little bit, you're gonna overshoot it. That's called hyperpolarization. But then yeah, it'll come back to normal. Okay.
But
So
yeah.
so now with that knowledge, right, we can see that the outside of the neuron is where there's a net positive charge, right? Because the inside of the
Yes.
neuron is going to have a net negative charge, right?
Yeah.
So so
But if K is a positive, then the thing would want more sodium so that it would be overall negative.
so yeah, that's what happens during this like, depolarization.
Mhm.
But for the resting, uh neuron, membrane potential, it's going to be at negative, right? And this outside environment will be positive. So electric field lines go from positive to negative. So that's why it's B.
Okay.
So explain that to me.
I just don't understand how that relates to like axon interior because we're just taking the sodium like and applying it to like CNS.
No, no. So tell me like why this would be it based on what I mentioned, what I said.
Well, you're talking about the different stages of this like diagram. So like first it's going up and the sodium is going out of this cell and then the potassium's going inwards and so that's how you get this part. But then when it's like returning like down here, it's net negative again, so that it has to return back to resting, which is like the negative. So this part is when potassium is coming in.
Yeah.
But
So okay. So we see that the neuron so axon is part of the neuron, right?
yes.
And so the inside of the neuron is negative, right?
Uh-huh.
And the outside is positive.
Yes.
And electric field lines go from positive to negative.
Hmm.
So B shows those electric field lines.
Okay. I get it.
Yeah.
All right.
Okay. Good job.
Honestly, you're not gonna like how I answer this. Myelin sheath
Uh-huh.
insulate. Sheath insulate. I don't know. I like made the connection and like because I remembered reading about like in
So
like
what's the
capstan of
point?
the axon.
What's the point of myelination?
Isn't it when there's like the separations and then it has to like jump
Yeah.
over and it creates the like junctions in between it so that it doesn't like
Nodes, yep.
yeah.
So yeah, since it
The nodes of Van Veer or something.
yeah. Very good. Yeah, since it jumps, it travels, that action potential travels, I believe, like 10 times as fast. I think it's like 5 meters per second max for like unmyelinated, and I think 150 meters per second for myelinated. Um, Myelination is also what white matter is compared to gray matter. Um,
Mhm.
and a lot of things like Alzheimer's, there's a lot of stuff with that, but like part of it involves demyelination. And and yeah, and then this passage is a great example of uh the AAMC just trying to psych you out because they're throwing all this information at you, followed by a really ridiculous looking circuit that they never even asked you any questions about. Oh yeah, they even have the depolarization and stuff. But yeah, that figure one of that electric circuit, they didn't like even ask anything about that. So
Yeah, it's 5 through 9. This is the second question.
uh-huh.
I
Yep.
think there's another one down there. Like,
Yeah. But yeah, you're a your ability to stay, focused and not let this.
Huh?
What's what's up?
Do you know when I saw this question, I didn't even read the passage first. I think
Sure, sure.
with these two, I literally didn't read it. I just went through them, and then here I kind of got stuck and I had to go read it.
Got it, got it. So, okay, let's see. Smallest substances. Okay. So,
And I was thinking, like, what are the smallest substances? I knew proteins was wrong right away, but I thought between
so remember when we talked about how
oh, I
atomic.
got it right. Yeah. Between sodium and potassium, I assumed that sodium was smaller because I looked at a periodic table and NaK and Cl are here. Na is the smallest. So that's why I picked B. I wasn't stuck on this. Sorry.
Wait, but be careful there because remember when we talked about ions?
Yeah, that they could all be the same size. I forgot.
So, so what type of ions would be smaller and what type of ions would be larger?
Charged. Um, losing the electrons would make it smaller, right? Because it doesn't have as many like rings,
Yeah, yeah.
valence electrons. So then
Mhm.
assuming that all of these are positively charged.
Well,
Well, Na is positively charged, Na plus, but K isn't potassium usually minus when it's in the NaK?
look at the periodic table.
They're right below each other, so they're both positive.
So
The
you,
periodic charge
if
would
you
be the
want to
same.
figure out if something's going to make a positive charge or a negative charge,
Well, it would want to go backwards towards these
yeah, rather than going forward
by 7, yeah.
to the krypton. So that's also why potassium we talked about in the neuron example.
Mhm.
So yeah, okay.
So
So that
it's an
means that,
electron.
what's up?
So it loses an electron. But chloride gains electrons, so that would be bigger.
Yeah, yeah. So compared to the neutral atom, the cation form will be smaller and the anion
Right.
form will be larger.
Right. So sodium, let's say a regular, no, but anyways, like a regular sodium versus a
Yeah, a regular potassium. The
no, but
sodium,
versus an elect a potassium with a positive charge, the sodium would still be smaller.
uh, sodium. When you say sodium, are you saying?
Normal, like non-charged sodium
Uh-huh.
versus a positively charged potassium, the sodium is still smaller.
I would say that the potassium ion would be smaller because the effect of losing.
But fine, but the argon is still greater than sodium.
So wait, argon greater than sodium?
Because it moved back one thing. So now it's this one.
Uh-huh. Wouldn't a atomic radius
But I
go?
know that all these trends, like this trend moves downwards and to the right, like size.
So you're gonna get either some trends going this way,
Yeah, but that's electronegativity and those ones. But like
or
size,
it's going this way.
and they go this way.
No, because
Not
that would count. You want the opposite, right? Because if we're saying that, this way is for some periodic trend, and this way is another periodic trend, then that just means basically that, I mean, it's not the opposite. So we can't say that, like for instance, atomic radius is going to be the opposite of this trend, because if
mhm.
it was this way, that would mean that, sodium is smaller than, or rather than iodine or something. If you're
But it is smaller than iodine.
It's larger because the trend is just it's up and to the right for all those things, and then down and to the left for atomic radius.
Isn't this value the mass number?
The 23 is the mass number, sure. But I'm
Yes.
trying to show you that if it was true that atomic radius increases if you go to the right and down, that would mean that, let's say, potassium compared to iodine, wouldn't that mean iodine is larger because it's to the right and below it, right?
But isn't it
No,
larger? I'm confused.
no.
When
So
did it stop being larger? I swear this is how it was taught in chem.
no, it's it it's not.
Okay, all right. Fine.
You're gonna go, like, just think of it in terms of like opposites. You can have certain trends go up as you go up and to the right, and then atomic radius will go up if you go down and to the left. Just think of them as
Okay,
opposites.
all right.
Because, like, the reason is if you're going to the right, you're increasing the amount of valence electrons, right?
Mm-hmm.
And if you increase the amount of valence electrons, that should make the size of something larger, because with all those extra valence electrons, the nucleus has a harder time pulling it all closer to itself.
Okay.
Yeah.
All right. Oh, because it's right next to. I understand. So because potassium is further. Wait. No. But now I'm thinking of it as iodine needs to gain. No, like to move there. Has to go up in charge. Versus potassium has to lose. So wouldn't iodine be greater based on like the amount of rings?
Sorry, I'm trying to. Okay. I sent
Yeah, I'm looking at it. It's both of them.
oh yeah, yeah. Open up, yeah, the latest one and
Mm-hmm.
share it. I'll show you.
I am showing.
I think you're just sharing your Chrome tab. Okay. So yeah, so here you can see that um I guess like the relative sizes of all these. And you can see that, you know, going to the left and down gives you larger size atomic radii compared to going up and to the right. So like this direction, everything gets larger, right? And then this direction, everything gets smaller.
Mm-hmm.
What I'm drawing is disappearing. Were you able to see what I was drawing?
I see it, yeah.
So yep, that's the periodic trend for atomic radius.
Okay. They're all popping up.
Yeah.
Oh God. All right. So I have to be more careful, but sodium was correct.
Yeah.
Okay, I was really confused here because I was trying to think of it from like a human body perspective. 0.1 meters seems, well, like I'm not even going to say anything about like 1 meter or 10 meters, but I don't understand how it can be 0.1 meters.
So
How would it be too short?
let's hide the solution so we can get a fresh kind of look at this. So let's first of all make sure we understand what they're asking. What are they asking?
So it's based off of this. It's the nerve conduction velocity test. And asking what is the closest distance the electrodes used in an NCV test can be placed on a nerve in order to measure the voltage change.
All right.
As a response to stimulus. And they have the like pulse travels at a speed of 100 meters per second.
So
And then
that's
you have,
yeah.
that's the speed, and then you have
Uh-huh.
the time.
Uh-huh.
And I think I have, when I was trying to do this, somewhere on the sheet. But isn't it you have the velocity from that because you started at 0 and you went up to 100? Or no, it's constant. So there's no accelerations.
Yeah, so we don't have to worry about that aspect, but if we have velocity and time, what can we get from those values?
Distance
Mm-hmm.
equals v over t.
Well, V over T would be something else.
Is it v times t?
Yeah, that can give you distance,
All
right?
right. Yes.
And so,
So 100 milliseconds.
well, where'd you get 100 milliseconds?
Sorry, 100 meters per second
Uh-huh.
times 1 millisecond.
Yeah, so the 1 millisecond,
I need to convert that.
yeah. So you could write 1 e negative 3 seconds.
Yes. Okay. And then the seconds cancel out
Good.
and you get 1 e to the negative first meters,
Uh-huh.
which is 0.1 meters.
There you go.
All right. So I have to actually use an equation and solve this out. I can't just like
Yep.
make a guess. All right.
Yeah, yeah.
I feel like I remember us doing a problem that was saying that like
Mhm.
you need resistance and potential. Like
Let's just treat it as, you know, something, so let's just so okay, what are they asking us here?
what information about an axon is required to calculate the current associated with an NCV pulse?
Okay, so we need to find current, right?
Pulse is in distance, so that's like either length or radius.
Wait, so let's just think about, okay, what are they asking us to find?
Information required current
Current, right? So now
equals
what
I over V, right?
yeah, Ohm's law. So V equals IR,
Uh-huh.
right? And
So that's resistivity. I is current.
mm, uh so it's weird. Everything I'm writing just disappears on my end, but it still.
Really? Can you see it through the like share thing? I see all of.
Uh-huh. Okay. That's
If
weird.
you then you share and maybe it'll fix it.
Yeah.
Okay. Try now. Do you see it?
Mhm. Okay. Yeah. So V equals IR. And so we need V and we need R. And R is resistance. Now, resistivity. So R we could also express as this.
Row length over amps.
Over area.
Oh, okay.
And rho is, yeah. Yeah, I know. There,
Too many.
I know. And then even with
Or
the,
used to be radius.
yeah, even with the row, it's not going to be density, so it's going to be another thing. But that this is
God.
called resistivity,
Hmm.
which is an intrinsic property of the material that you're using,
Hmm. So
right?
it's a constant.
Mm-hmm. Yeah. So oh, and then conductivity is the inverse of
Resistivity.
resistivity. Yeah.
Okay.
Now, so okay, so we need, as you said, so like V over R is equal to current. So we need voltage, we need resistance, right?
Right.
So A says conductivity, resistivity, and length. Is that going to help us?
No.
B says potential. When they say potential, what do they mean?
Uh, like potential energy.
Um, so like in this context.
Um, MGH.
So that's for gravitational potential energy, but um,
MH.
so
Mass acceleration and height.
so in electrostatics and circuits and stuff, uh the potential is voltage.
Hmm.
Okay.
Yes.
So we definitely want voltage, but then they give us conductivity and radius. Now, conductivity, if we inverse it, we can get resistivity, and radius we can get area from, but we're still missing length, right?
Hmm.
So this won't work. C, yeah,
Isn't this length?
uh-huh. But
But then we don't have resistivity like in D.
oh, so wait,
Like
we
we
just did,
so that's why I thought that like potential and then resistivity. Well,
so
I didn't know there was a distance between resistance and resistivity,
yeah,
but radius is length,
uh,
diameter is length.
no, so radius is going to be giving you an idea about the area.
But isn't that a good thing? Because that's part of this equation.
Yeah, but if we have, so they're giving us voltage, resistivity, and radius, which means that we can find the area, but we don't have L,
Mm.
right?
Okay, so this one we have voltage R, and that's all we need. So length is unnecessary.
No, no, no. So we have voltage, and then we have resistance per
Oh,
length,
like
and then they give us length.
cross that out with length. You cross out these values and then you just get resistance.
There you go.
I understand. Okay.
Mm-hmm.
This one was super cool because I remember that you taught me the log thing
Oh
for,
yeah.
well, I don't know if you taught me, but I did the log thing, so then I did the inverse log and I got 5.
Mm-hmm. Great job.
And then I thought about like the pH scale and that it would be a weak acid because it's close to neutral.
Mm-hmm.
And then here, did I get this one right?
I think so.
Okay. So looking at it, I was like, I can't remember which one I knew was the base. I'm gonna assume. Wait, but how did I know that? I knew that they were different,
Uh-huh.
but I didn't know what an oxyacid was.
Mm-hmm.
Can we go over this, please?
Yeah, yeah, yeah. So um so they most likely mentioned it in the passage, but it's basically it's an acid, or with oxygen in it. Okay, so here we go. So oxyacids or bases, the oxyacid would be something like that, and the base would be something like this. So, and then they talk about this general formula here. That's the oxyacid formula. So basically,
Where does it say that that's an oxyacid?
oh
Or
here,
I just need to know that.
oh,
Oh, or bases, but it doesn't help us.
mhm. So we want, so for the oxyacid, right? It must
Mhm.
look like this, like A O
Oh,
M
I
O.
get it. And so this is an oxyacid because it's NO.
Yeah, the A here is the
And
N.
then this one was a base because it doesn't have the oxygen.
This would be the base, right? Like
Yeah.
hydroxide.
Yeah, and same here.
Yep, you just replace the calcium part with the nickel.
Perfect. Cool.
Hmm.
Easy enough.
Yep.
All right. Isn't it like the trend?
You're saying for an unknown one? Yeah, sorry.
Unknown is A, so it's either this or like it's either the base or the oxyacid.
Uh,
And
yeah, it seems like if it's making the base, it's a metal. If it's making the oxyacid, it seems like it's the nonmetal.
yeah, it's
Oh yeah,
this.
there it is too. Yep. So there,
But we just figured out that it was acidic. So then
yep,
even if it's a weak acid, I said that it's a non-metal.
excellent. Good job.
Okay, squalene is like, in my eyes, it's like there's like a chemical like that you use in derm. It's supposedly like good for skincare stuff. Like a lot of skincare has squalene. And
Uh-huh.
then I was thinking about like what have I heard as far as like skin stuff goes, like that you put on your skin. And I thought that like
What about
that
hyaluronic acid?
yeah, like hyaluronic acid, but I didn't think that steroid hormones like go into hyaluronic acid. So like I was looking at it and I was really deciding if it was C or not, and then I thought that A was a safer bet.
So okay, so triacylglycerols, like, so these are also like examples of things to know, like what like they look like if you're able to draw them. So I'm gonna just write down question 14.
Well, it's three, try, and then these are both
Yeah,
try.
but I mean that you could say like, it can say like tricycle, and you're gonna be like, all right, that could be it.
Okay. Well,
So yeah, so like I just wrote it down.
you're the one that always says to make the language connection.
No, yeah,
And
yeah.
I make
But
it and you yell at me.
no, I'm not yelling. I'm sorry. I'm sorry.
I know, I'm kidding, I'm kidding.
I'm just saying the try is it's like it's like you're
The most
gonna
common
know
thing.
you're gonna know that it means three, like no matter what, right?
Yeah.
But the acetyl part you should know, the glycerol you should know, like what those look like. Um, so like a glycerol looks like this, right? And then you
A.
can have fatty acids like this that can bind to the glycerol to give you the triacylglycerol, aka fat.
Mm-hmm.
So that's
What's
more
the difference
like
between triacyl and triglycerol?
those are the same, yeah. Same thing with triglyceride.
Hmm. Okay.
But yeah. Now if you so that means so if we had three of the fatty acids, right? Now if we had two of the fatty acids, but one of them was a phosphate, that would give you the phospholipid.
Hmm.
And then yeah, go down. And for prostaglandins are made out of arachidonic acid.
I
And
don't even know what that is.
yeah.
A rock. Isn't that like a
And
spider? These legs do spiders have?
yeah, look at you. Yep.
I don't know. Eight?
Wait, what about that?
These spider legs do spiders have?
Uh-huh. Um, yeah. So
That doesn't really help.
yeah, no, that's good, but yeah, good work there. With the arachidonic acid. But yes, so steroid hormones that come from cholesterol have that, structure like, I think it's like something like this. Like the 4-ring structure.
Mm-hmm. This is which? Triglycerols
Oh,
or prostaglandins?
so this is the cholesterol, which
Okay.
is where all the steroid hormones come from. And if
Okay.
you go up to the squalene, you could see that all you need is boom, 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 and boom. You get your cholesterol precursor of steroid hormones there.
Okay. Cool. See, I thought I did this correctly. I like had a whole formula, like I was doing it the way that we went over to do it. I'm like actually not happy that I got this wrong.
Uh, it's probably something with like a well, okay, let's see. Concentration of Cl minus in a 0.1 m solution of calcium chloride. Okay, so
Why does it have to be doubled?
yeah, so
Divided.
hide the solution for a sec.
Okay.
So uh, let's think, right? So what does this look like if we were to draw it?
CaCl.
So
So you have to go and find both of these. So you have Ca, which is 40, and Cl,
so
which
we're
is
not. So that you're looking at So
we're looking for Cl within that.
yeah. So
Yeah.
what kind of ion do these make?
Like charge wise?
Yeah. You can look at the periodic
Isn't it +1,
You can look at the periodic table.
2 plus, and this is -1.
All right.
So it's 1 plus overall.
Yeah, but it can't be like that, right?
Right.
Like it has if it exists as calcium chloride. So you see calcium here, it goes 1, 2. So it turns into Ca2 plus.
Right.
What
But
about
Cl is -1.
-1? So calcium chloride can't just be CaCl, right?
It's something with a -1.
No. So CaCl can't exist because it'll still have a +1 charge.
Uh-huh.
So what could CaCl look like? Like what could calcium chloride look like then?
An oxid.
Mhm.
No.
So that
Okay, yeah, because then you would have -2. All right.
so if you're given a substance, right? If I
That
say
can
that
exist in nature, I have to convert it to something that it can exist as.
no. So if you're given any molecule, right? Like instead of an ion, if you're given a molecule, it must
It
not
would
have a
balance the equation.
wait,
Okay.
what?
Like balance the thing.
No. So listen, so if you have a compound molecule, unless it's an ion, if it's an ion, they'll tell you, right? But unless it's an ion, it's gonna have a net charge of 0.
Mm-hmm.
So like have to take that into consideration when you like write what the actual thing is, right? Because Ca2 plus, Cl minus, when they're combined, we need to have it no charge, no net charge. So we need 2 of the Cls,
Okay.
right?
Yes. So then I need 2 of them and it's doubled to the 0.1 moles. So then it's 0.2 moles. Is that what's happening?
Yeah.
Okay, so there's no calculation needed. It's literally just looking at, okay.
Well, the big thing here is being able to see calcium chloride and write it down. That's really big.
Understood. Okay.
And then this is the reducing sugar thing. And
What is the shiny deposition of a shiny silver mirror on the
yeah,
wall?
so there's like two different tests that you'll see. Uh, I think there's Tollen's test, there's Benedict's test, I think. Anyway, one of them, they're tests for reducing sugars, um so one of them uses silver, another one uses copper. And so if a reducing sugar is found, the silver uh
Will reflect.
the silver will turn into a solid, and that's what they mean by the mirror, the silver mirror. Um, and then the other test would be like with the copper thing, and that'll into like a reddish kind of brick red kind of color. But yeah, these are just tests for reducing sugars. So we need to find which is a reducing sugar. And so if it's a hemiacetal or a hemiketal, you're going to get it's going to be reducing. Like, but if it's a ketal or a acetal without the hemi, it's not going to be reducing. So you could hide the solutions just so we can get a chance to see everything fresh with the fresh eyes. So now, if you have this as a functional group, this is a hemiacetal. Okay. And
Why is it a hemi? Like, what about its structure makes it?
I see. So, um,
What
so
is
it's
the
mostly
hemi?
mostly this part over here, the top part, like if it's bound to an OH and an OR group. So if we just had a regular, glucose like this is your OR, your OH, your R, and your H,
Okay.
making that hemi. And it can and it's a reducing sugar. It can reduce other things, which means itself can be oxidized.
Mm-hmm.
But when you have a glycosidic bond form like that, we still have the R, we still have the H, we still have this OR, but we don't have the OH anymore. This turns into another OR. So now this is not a
Like
heavy.
acetal?
What's up?
Pseudoacetal?
Oh,
You said,
just the
oh,
version of the hemi, but without the word hemi. So it's just an acetal. And now these cannot be reducing sugars.
right. So I have to look at something in the structure. So it would be these ones. Like,
Yeah.
is this cross?
So
One,
like
two.
shortcut would be that glycosidic bonds are never going to be reducing because we don't have any free OH group. But yeah, but these at the ends, right, could be at least these three
Mhm.
are hemiacetals, right?
So this one doesn't have it.
So yeah, this is the only
Has-
one where it doesn't have, it just has this alcohol group attached to like the CH2 here. So yeah. So
So,
A, B, and C.
sucrose?
Yeah. So
So the answer is sucrose.
the answer is sucrose. Yeah.
Okay, cool. Do we
Cool.
need to stop?
Let's do one more.
Okay. Yeah. I have no idea what the charges of these amino acids are, so
So okay, so that's a quick fix. So basically, like, the first like two things uh in terms of amino acids and how I teach it is
polar
charge.
charge.
And these include the 2 acidic and the 3 basic.
Um,
Yep.
ASP, aspartic and glutamic acid,
Good.
and then glutamine and asparagine.
Close. So those are the same things as the acids that you mentioned, except in amide form.
Those are bases.
So those will be just polar.
Okay.
But the bases are going to be
And
histidine.
then there's 3 positively charged.
Yeah, those would be the bases. So that's histidine, arginine,
Nice.
lysine.
How many times have I written out this list? I think it would be a fun drinking game.
So uh
Every time to read it.
mhm.
So,
Yeah, they even wrote amino acids can't go far without them coming up again. But yeah, we only
no,
have an arginine here that could be charged, and so there you go.
lysine, arginine, and histidine, right? And then what's the second group? Polarity?
Oh yeah, which I call partial. I mean, this is not
Partial.
what I call it, but partial charge. So that'll include the STY that participate in phosphorylation. And then the amide forms of those acidic amino acids. So
Leucine is non-polar, right?
correct.
So it's a 0.
Mm-hmm.
And alanine is in the same group.
Yep.
So
Leucine.
arginine is -1, leucine is 0, 0. So these two cancel each other out.
Oh well. So
If you calculate charge,
yeah. So
so -1, 0.
these are all non-polar, so they don't have charges. But arginine is basic, so it has a plus
Oh,
charge.
right.
Mm-hmm.
Okay, yeah. So it's +1. So phenylalanine also doesn't have a charge?
Correct. It'll just be the you know,
So if
glutamic
it's
acid.
not SPY or those 5, it has to be non-polar.
So the charged ones will be acidic, E and D, and then basic, histidine, arginine, and lysine. Then partial charge or polar would be STY. And then if you take this glutamic acid and you turn it into an amide, it turns into glutamine. So that'll be another polar one. And then the aspartic acid will be asparaginine if you turn it into an amide. And so that'll be
N.
EN. Yep. And so we have 5 charged, 5 partial. So that's 10. And there's 20 in total. So the rest of them will be nonpolar.
What's the thing for arginine? The one letter?
Oh yeah, I think it's what you said, N. Oh
No,
wait,
that's
what are we talking
I
about?
meant
That's
for
asparaginine, my bad. Arginine is R.
R. Okay, that's what I thought.
Yeah.
Okay.
Good.
All right.
So I would say to
So,
yeah.
I mean, do you really think I should take another one tomorrow? You don't think I should do like a blind review and go over because I haven't done that yet.
Yeah, I think you should do another one tomorrow just because we want to
Number
be
up.
able to do it like because weekends are the only times that we can do like, a full length like that. So, I mean, if you want, you could do it like maybe Sunday if you want, or
It doesn't really make a difference between tomorrow and Sunday. Sunday I have like meetings and stuff, so it'll end up being busier.
Okay, okay. Yeah. So so yeah, I would say to take another one. I know it's super soon, but we just want to
But
make sure
like
that we take
there's
advantage
no
of that.
draining, so like to do one and again tomorrow just feels so soon. But I get it, it's my own
It
fault.
is soon. It is it is soon, uh but you're killing it, you're doing an excellent job, and let's just nail that
But
down.
like keeps that trend going.
Yeah, yeah, because we wanna have as many, tests to bolster like that score, as much as possible. Because I want you, like, now I think that you're on track to even score even higher, but yeah, we don't wanna, like, you did excellent. Like, I'm very, very impressed and happy about that, but I don't want this to be like, okay, I'm fine, so I don't have to do any more, work and
I
stuff.
like I was actually like when you said 5'11", I'm shocked. Like I
Uh-huh.
feel like
Yeah, yeah. Yeah, and a perfect cars section. So, like, see how like what I was saying, like, you don't need
physics.
the cars here. Um, but I think that, like, the idea behind having you do all that physics stuff was to put yourself into the mindset of how a physicist or a physics person thinks, because you saw that those are the types of people that, those majors get really high scores in on the MCAT, like all in all
I
sec.
think we needed to BB. It felt really hard yesterday.
What's up?
BB felt really hard yesterday, so I think we need to spend some time reviewing that.
Oh yeah, totally, totally. But I think that, yeah, the foundation that you have in, like, the physics stuff, like, the reason I wanted you to, well, other than the
Yeah.
fact that that was like those were the weak spots, like, that getting good at that and being able to think in a critical way like that means that you're going to be improving your score in all of the sections. And I think that's what we saw. So I would say, yeah, I would say, to take one tomorrow. I know it's going to be tough, but next week we can make it so that you don't have to take one on Thursday, and you could just take the next one on, the next weekend. But really want to make sure that we can cement this. So I want to see, like,
Do I even have next weekend?
what's
Yeah,
up?
I have. You're right.
What's up about next week?
Never mind. Sorry.
Yeah,
I,
yeah. So yeah, it's gonna be tough, but yeah, just crank it out tomorrow, and then next week you don't have to do one on Thursday. You could just do it on, a week after, so you'll get, more time then. But yeah, I think that, we're in a very good spot now. We just want to make sure we can replicate that. Um,
yeah. All
and
right.
yeah, but yeah, you're congratulations, you're doing really awesome.
All
So
right. Okay.
yeah, it's
So
gonna
like,
suck,
what do
but
I
yeah.
do with reviewing? How are we gonna review this test and the next one?
So I guess if you have, like, time today, you can review it, like, as much of it as you can, but you might not be able to review all of it, of course. So, and you'll take your,
Not do a blind review, do like an actual, just review it.
oh, no, no, we could just have you do as much as you can today, and then tomorrow you take that next test, and then
Then we
after
review
that, because next week we're gonna have, like, a lot of time. So next week we can go over uh both tests,
Sounds good.
basically. So you're going to take,
Full length one.
okay, and let's see.
Then I'll do two next Saturday.
Okay, all right then. So
All right.
all right, so I guess I'll see you on Sunday.
Yeah. At 7. We have it set.
Yes. So
All right.
yeah, you're killing it. So
Thank you.
keep it up, okay? You're really making it.
All
So
right.
all right, awesome. So good luck. Yeah, good luck tomorrow, and I'll see you on Sunday, okay? Take care.